Welcome. Here we're going to be looking at computing net accumulations or Riemann sums for a particular function. So let's go ahead and start with an example. I have capital F prime of x equals x squared plus 1. This capital F prime, this is some new notation that is introduced to this unit. What it really means is that this is a rate of change function. So the fact that you have that prime there is telling you this is a rate of change function, and that's what we need in order to calculate the net accumulation. So it must be a rate of change function in order to do this process. So let's go ahead and begin. I'm going to start by sketching over here in the upper corner just kind of what this graph looks like so that I have something to work off of, because I tend to be very visual and I like to see what I'm looking at. So here is my x and y axis. X squared plus 1 is a parabola facing up with the vertex here at the point 0 and 1. And I am interested in 1, 2, 3, 4, 5. So I'm sorry, the interval that I'm interested in here is 1 to 5. So this is kind of the area that I am attempting to find. So that's my zone of interest. And I'm going to estimate that area using Riemann sums, or these left, right, and midpoint approximations. So I like to start always by finding what my delta x is. So my problem statement, let's see. Oh, I need to decide what I'm going to do. So we're going to find L5, R5, and M5. So that lowercase, or that subscript, that number tells you how many intervals you have. So I have 5 intervals, and I would like to find the width of each of my boxes. That's delta x. So delta x is b minus a over n. I know that n is 5 because that's my subscript here on my left, right, and midpoint. B will be, this format of this interval is in the format a comma b. So I have all the pieces I need. It will be 5 minus 1 divided by 5, which is 4 over 5. And I'll write that as a decimal as 0.8. So that's my delta x, that's the width of each of my little boxes. And we're going to start by doing the left-hand Riemann sums. So that will look like this. I will have little boxes. I'll be using the left-hand side of the box as the height, and that will let me approximate my area under my curve there. So I like to do a number line. I'll start with my lower limit, which is 1. I'm going to go ahead and increase and just do 5 lines, because I know I have 5 intervals, or 5 subintervals. So I'll do 1, 2, 3, 4, 5, which gets me my 5 little intervals here. The last one is going to be 5, and then the numbers in between will be increasing by my delta x. So I'll have 1.8, 2.6, 3.4, 4.2, and then 5. So those are the x values that are going to define my intervals there. The next thing I like to do is calculate the heights at each of those points. So I will need all of these numbers in the process of calculating both my left and right. So I'll just do all of them to start. I'll start with 1 and I'll move up my number line until I get to 5. So I am calculating the height at each of these locations by plugging the x value. So I'll start with 1, and I'll be plugging that into my formula here, which is x squared plus 1, so that'll be 1 squared plus 1, which will be 2. F prime of 1.8 will be 4.24. F prime of 2.6 is 7.76. F prime of 3.4 is 12.56. F prime of 4.2 is 18.64. And F prime of 5 is 26. So I now have all of these. There are 6 of them. And for each of my left and right, I'm only going to use 5. So for the left point one, I'll use the first 5, 1 through 4.2. For the right-hand approximation, I'll use the last 5, which will be 1.8 through 5. Those will be the heights of my boxes, and I will multiply the heights by the widths in order to get my approximation. So if I'm working on my left hand, L5, this will be the height of my first box, which is 2, times the width, which is 0.8, plus the height of my second box, which is 4.24, times my width. The width will be the same for every single box. Once you've decided on the width, it's the same because you define that based on your interval and the number of boxes, subintervals that you're putting in. The next will be the height of my third box, which is 7.76 times 0.8. My next will be 12.56 times 0.8. And I apologize, I've run out of space here. I was trying to fit it all on one screen. My last one will be 18.64 times 0.8. So I'll add those all up together. I'll leave that to the viewer to add those all up together because that's just arithmetic at this point. But all of those things added together will be the left-hand approximation, the L5, for this particular scenario. For R5, let me scooch it in a little bit since I ran out of space in the last line. I will take the last points, the last, the second half. So I'll start with 1.8, the value at 1.8, which is 4.24. That is the height when the x value is 1.8. I'll multiply that by my width, and then I'll proceed. So then I have 7.76 times 0.8, 12.56 times 0.8, 18.64 times 0.8, and 26 times 0.8. And that will be my right-hand approximation. So what I'm doing with the right-hand approximation, and I just want to draw it so that we see, my left-hand approximation, if you see here in the blue up in the upper right corner, I took the height of each box from the left-hand side of the interval. But for the right-hand approximation, you go instead to the right-hand side of the interval and you draw out that way. So the right-hand approximation here, I start on the right-hand side and that becomes the height. So it's similar. It just depends on how we're defining, or really where we're taking our height, which is the y value, which is the function value for a particular x term. So that is the left and right hand side. Let's scroll down to a new page and we'll do the midpoint because it's a little different. We're going to use still the same delta x, but our y values, our x values will be different. So I'm going to recopy for M5. I'm going to recopy my number line. And here up above in the upper left corner, I was pretty close together. I'm going to give myself more space. So I'm going to do 5 intervals, but I'm going to make it more spread out because I need to do the midpoints. So I need room to write. I still have my 1, 1.8, 2.6, 3.4, 4.2, and 5. Those values I'm going to leave because those define the edges of each of my intervals. In between each of them, I'm going to do the midpoint. So the midpoints here, halfway between 1 and 1.8 is 1.4. Halfway between 1.8 and 2.6 is 2.2. Here halfway is 3. Here halfway is 3.8. And here halfway is 4.6. So you can do this using your logic and just saying, okay, well, halfway between 1.8 and 2.6 is 2.2. But also, once you have defined the first of the midpoints, you can add delta x to get the next one. So 1.4 plus 0.8, which is my delta x for this problem, is 2.2, plus delta x is 3, plus delta x is 3.8, etc. So if you don't want to do the halfway point for all of them, you can just find the first one and then add delta x repeatedly to get where you want to be. But once I've done that, then I kind of have this new number line. And again, I'm going to do exactly the same process as I've done before, but for m. So m5 is going to be the function evaluated for 1.4 times delta x, which is 0.8. The next will be the function evaluated for 2.2 times 0.8. We will do the function evaluated for 3 times 0.8, the function evaluated for 3.8 times 0.8, and the function evaluated at 4.6 times 0.8. And remember that the function was given in the problem statement. We've been using it all along, is x squared plus 1. So that's what I will be plugging in. I will plug each of these midpoint values in for x. And then I will do the arithmetic, and that is my midpoint approximation for this particular scenario. Thank you so much for watching.